So the next speaker is Omry Ginzburg. Comprehensive turbulence as a new channel for the formation of giant clumps at high redshifts.
Okay, can you hear me? Okay, so hi everyone, I'm Omry from Labour University. I looked at the beginning of the talk for an animation of a phoenix rising from the ashes, because this, for many of you who maybe have been in before, 8 years ago, this is not the first time that this issue is raised here, but it rose from Neil's desktop drawer a year ago, and we decided to dig into this again. So I want to tell you about a different, so we heard from Florent that you can have clumps without compressive turbulence, but in cosmological settings it seems like the formation of clumps by tumor instability might be subdominant compared to other channels. So I want to start with motivation to talk about two properties of star-forming disks at what today is intermediate redshift and not high redshift. The one is the supersonic turbulence. This is a very robust result that we have galaxies with supersonic turbulence locally can reach very high values of 200 kilometers per second. Globally, galaxies can reach at redshift 380 to 100 kilometers per second velocity dispersion. The other property is the perturbed clumpy structure of star-forming disks at high redshift. Again, we see the Candace observation. This is the Vela simulation. You can see how all of these star-forming disks are highly perturbed and clumped. For supersonic turbulence to really be a robust, observable, and not to decay rapidly as theory predicts, it must be driven somehow. And as it turns out, a very common way to keep supersonic turbulence alive and kicking is by the fact that the galaxies are clumpy. So there's a really intimate link between these two phenomena. And the linking mechanism is the tumor instability. So let me remind you, tumor instability is governed by the tumor Q parameter, which represents a competition between two pushing forces. The velocity dispersion represents pressure, kappa or rotation or angular velocity represents the shear. And these two compete with gravity represented by the surface density of the disk. When Q is below 1, the disk is gravitationally unstable, and the galaxy starts to fragment into clumps. So the concept of disk self-regulation is built by the following qualitative argument that is very nice. If we look in a cartoonish way as a Q as a function of time, and we draw the Q equals 1 line here. And let's think that we have a star-forming disk that starts with a value of Q that is slightly below unity. The disk becomes gravitationally unstable, starts to fragment into clumps. The disk becomes very asymmetric. The clumps are very dense, they have intense star formation, and the asymmetry in the disk applies torques that drive, as we heard from Juba, a mass transport down the potential well due to the angular momentum flux outside. What I argue is that these two mechanisms, and possibly more, are responsible for driving turbulence. For supernova fieldwork, this is maybe more obvious. This is a nice simulation this is Starforge, I think, by Mark Gurdich. You see inside these star-forming regions, all hell breaks loose with a lot of jets and shocks and supernovae. And all of this energy goes back to the ISM and can efficiently drive turbulence. For transport, it might be slightly less obvious what I mean by that. And what I mean by that is that due to the radial mass transport within the disk from the torque, we have a conversion from gravitational potential energy to kinetic energy when the mass goes down the potential well. And this is another source of kinetic energy that can go into turbulence. So these two together, and maybe by other mechanisms as well, they drive turbulence, increasing the velocity dispersion, eventually bringing Q above unity. Disk becomes settled, less violent because the gravitational stability weakens. We have less clumps, less torques, weaker transport, weaker feedback, and the disk is able to, and the turbulence dissipates quickly, bring again Q below unity, and this cycle continues above Q equals 1. This is where the concept of disk self-regulation comes from. So there is a kind of a feedback loop between the dynamics of turbulence in the disk and the gravitational instabilities that allow this long-lasting, clumpy, turbulent state. Now, these kind of models that assume this have been very successful, I don't know, very successful, but they were able to match some observations. This is a result from my work with Avishai Nir and Mark Rumholtz, but Mark also did that before. If you look at for example, the velocity dispersion versus star formation rate, and the curves are some models that use the concept of self-regulation, you get a general agreement. If I put the error bars of these observations, you will not see anything anyway. The model, the key concept in the models is that they assume this self-regulation about Q equals 1, and this sets a threshold for clump formation. However, when we go to cosmological simulations, we find that this is not necessarily the case. Clumps, at least in the Villa simulation, appear to form in regions where Q is well above 1. This is an example sequence of one of the Villa galaxies. And you can see the different snapshots following the evolution or the formation of a clump. So on the left, you see the surface density. On the right, you see the Q parameter in log. And you can see if you go back to the moment where the clump has just started to collapse, the Q value in surrounding is well above 1, 3, or in some regions even more. And it's only when it becomes really, really dense and really collapsed is when its Q parameter goes below unity. But at these regions, the surface density is so high, so you're well beyond the linear regime where Tumre applies. If we look at several other galaxies, at the distribution of the Q parameters in protoclump regions that are about to form clumps, yeah, this is, again, I forgot to mention this, again, see how old this subject is, by Shigeki Inouye. We find that many, many clumps, if not the majority of the clumps, form in regions where Q is above 1. So it seems like it's not Tumre instability, it's something else. If Q is above 1, how do these clumps form? So if we go back to the expression for Q, so we have kappa, which is usually more or less set by the potential well of the dark matter halo. We have the surface density, but we also have sigma. If we can make sigma very, very large, for Q to go above unity, but make it very non-isotropic in the sense that most of the velocity dispersion, most of the velocity field tend to converge towards the point, we can have a very large Q, but the local velocity field will converge towards the point, and eventually the region will become dense enough for gravity to take over. So this is the idea we pursue, and the way we do it is we take the velocity field and compose it to a solenoidal part and a compressive part. There are a few ways to do that. We do it in one of the ways. If you're interested, I can elaborate later. And it has been shown that if you have excess of compressive modes of turbulence, the simulation of a turbulence box by Christopher Dera et al., your density distribution reaches much higher, it's much broader and can reach, just by turbulence, make regions very, very dense. So this looks like a viable mechanism to make regions dense enough to eventually allow self-gravity to work. So if we look at the same sequence I've shown you before, but now we look at on the right panel, instead of Q, you see the fraction of total energy in turbulence that is in a converging mode, compressive mode. This is the same sequence I've shown you before, and you can see how this clump, as it collapses, most of the turbulence in its region is more of a compressive nature rather than a solenoidal nature. And eventually, it is dominated by rotation, as we've seen from Avishai's talk, that these clumps in the simulations are eventually becoming rotationally supported, but the initial collapse is initiated by the compressive mode. And if you look at the distribution of protoclumps compared to other regions of the disk, we indeed see that protoclump regions in the Villa simulations form in regions where the fraction of energy in turbulence energy is more of a compressive nature. And more interestingly is if we go to isolated simulations, we don't see any difference between random regions in the disk and protoclumps, and all of the clumps form in regions, or most of the clumps form in regions that are not necessarily dominated by converging flows. So it seems like in the Villa simulations we have axis compressive modes of turbulence in protoclump regions. Now why is that? So this is two movies. This is a Villa simulation. This is just an isolated galaxy. And two major things that you can see different from here and here is that this galaxy is fed by streams, this galaxy undergo mergers, while this galaxy just evolves by itself. So the ideas we want to pursue on the origins of the excess compression is the fact that in cosmological simulations we have environment that may induce gravitational tides, and the fact that we have interaction between the streams and the disk. So if we pursue the idea of gravitational tides, this is from Flora a few years ago, 10 years ago, showing this is a simulation of a merger, and you can just look at the top panel, which shows the energy fraction in compressive modes compared to solenoidal modes. So compressive in green, solenoidal in blue, and you can see how, as the merger evolves, the fraction of energy in compressive modes become dominant over solenoidal modes during the event of the merger, and then it settles back to an equilibrium. So we wanted to test this also in the Vela simulations. The way to quantify it is to take the tidal tensor, which is a second derivative matrix of potential, diagonalize it to get three eigenvalues. A negative eigenvalue, what you usually think about tidal stripping is, well, the local tidal field has an expansion along or disruption along the relevant direction. If it's positive, it's compressive along the relevant direction. Now, most people think about tidal stripping, but it is actually very feasible, realistic, and physical to have a fully compressive tidal field, where all of these eigenvalues are positive, meaning the tidal field is fully compressive. I came up with this measure of how compressive the tidal field is. I'm not going to talk about where this comes from, but if we look again at the distribution of this value for protoclump regions versus random regions in the disk, we see that these protoclump regions form in regions where the tidal field tends to be more fully compressive compared to fully disruptive. Or not fully disruptive, partially disruptive. For disk stream interaction, we used the same method that you saw from Dubos talk about because in Vela it's an Eulerian code. It's hard to track where the gas comes from, but we can roughly get an idea of what cells contain significant mass from streams. And what we did is we went to protoclump regions. So this is example, this is the same snapshot I showed you before. You can see this is an incoming stream. So what we said, okay, let's look at the region where this protoclump resides. We compute how much mass it has in streams, and we compare to the average mass in an annulus of the same radius. This can tell us if this region is special compared to the other regions with the same radius. And again, if we look at this distribution of this value of this quantity, again, the mass in this angular bin compared to the average mass in the same annulus, you can see again, if you compare protoclump regions to random patches, that protoclump regions tend to form in regions where the stream interacts with the disk compared to random patches. So to summarize, I have two questions. Is the tumor instability a complete theory in cosmological settings? I'm not going to give an answer to that because I don't know, but I don't think it might not be because we saw that in Vela, clump seems to also form in tumor stable regions, and you saw from Dubos talk that this theory might not explain totally the radial velocities. And what stirs compressive modes in cosmological galaxies? Well, gravitational tide is one possibility. We have a hunch that streams might be the dominant one. Am I going to put a third question that I'm not even going to try and answer is, do we need a new theory from clump formation? Maybe yes, maybe no. Thank you.
questions? Florian?
Thanks and congratulations for this fantastic work. I have 20 questions and 5 comments. So maybe I will focus on one. So you show that where the turbulence is compressive, then it will eventually form a clumps later. So how do you define how much back in time you have to look, and at which scale you have to select these regions to measure your Q parameter?
So I'm going to tell you how we did it, and you can. It's not difficult. It's not easy for several reasons. One, we don't have trace of particles in Vela, so we cannot really know where the gas that eventually collapsed, where did it come from. But what we did, we just took the first snapshot, we identified the clump, and we extrapolated one snapshot back using the velocities inside the clump. The region, this is also quite not well defined. We tried 500 parsec, 1 kiloparsec about the center that we defined, and the results are not that big.
Quick question, quick answer. And the next speaker should approach to the desk.
How long is the lifetime of this clumps formed by the compression?
Okay, so they can be very long-lived. Wanted a short answer. They can live for gigayears. Okay, they can be short-lived. They can be long-lived. We find both short-lived and long-lived clumps that are formed via this mechanism.
Okay, let's thank Omry again.